back, students. Today I am going to teach you theorems in functions which are useful for your final examinations. Theorem number 1. If f a to b, g b to c be bisections, then prove that g circle of a to c is also a bisection. To prove this g circle of a to c is a bisection, we have to prove two results. Number 1, if a to b, g b to c bisections, then g circle of a to c is also 1 1 and on 2. In that first one is we have to prove f a to b and g b to c are 1 1. G circle of a to c. Now I consider two elements in the set a1, a2. Then the images of a in the set b becomes f of a1 and f of a2. And again if the function g b to c, then here the images of f of a1 and f of a2 will become g of f of a1, g of f of a2. Now it is obvious that g circle of a to c, that's what I have written here. To prove that g circle of is 1 1 function, consider two elements a1, a2 belongs to a. F of a1, f of a2 belongs to b. G of f of a1, g of f of a2 belongs to c. That is g circle f of a1, g circle f of a2 belongs to c. Now let us consider g circle f of a1 is equal to g circle f of a2. You can write it as g of f of a1 is equal to g of f of a2. And also g of f of a1 becomes f of a1, g of f of a2 becomes f of a2 since g is 1 1 function. And also f of a1 becomes a1, f of a2 becomes a2 since f is 1 1. Hence g circle of a to c is a 1 1 function. Next we have to prove g circle of a to c is onto function. What is the definition of onto function? F a to b, g b to c are onto functions. Now we have to prove g circle f is also onto. Let c belongs to c. I am considering the element c in the set c. Since g b to c is onto function, there exists b belongs to b such that g of b is equal to c. Since f a to b is onto function, from the definition of onto function, there exists a belongs to a, then f of a is equal to b. Now g of b is equal to c, as we have written here, g of b is equal to c. G of f of a is equal to c. And you can write it as g circle f of a is equal to c. For all c belongs to c, there exists a belongs to a such that g circle f of a is equal to c. Hence g circle of a to c is onto function. So from these two results you can conclude that from 1 and 2 g circle of a to c is also a bisection. Got it? Next I am going to discuss another theorem. If f a to b is a bisection, then f inverse circle f is equal to ia and f circle f inverse is equal to ib. F a to b is a bisection, so its inverse function f inverse b to a is also a bisection. By the definition, f circle f inverse b to b, f inverse circle f a to are also bisections. Now we know a to a is identity function, ib b to b is also identity function. So from these three figures you can understand the topic. To prove that, first one, f inverse circle f is equal to ia. A belongs to a, b belongs to b such that f of a is equal to b implies a is equal to f inverse of b since f is a bisection. F inverse circle f of a is equal to f inverse f of a, that is equal to f inverse of b because f of a is equal to b. And we know that f inverse of b is equal to a, which is ia of a. F inverse circle f is equal to ia. To prove that, f circle f inverse is equal to ib. A belongs to a, b belongs to b such that f of a is equal to b implies a is equal to f inverse of b. We know this definition. Now I am taking f circle f inverse of the element b. F of f inverse of b. Now f inverse of b can be written as a, that is f of a, which is equal to b, that is equal to ib of b. Therefore f circle f inverse is equal to ib. Next one is another theorem I am going to discuss. If f a to b, g b to c are bisective functions, then g circle f whole inverse equal to f inverse circle g inverse. If a to b, g b to c are bisections, now g circle of a to c is also bisection. Already we proved this theorem. Now I am taking g inverse c to b, f inverse b to a are bisections. F inverse circle g inverse also c to a is also a bisection. For all c belongs to c, there exists b belongs to b such that g of b is equal to c. That is onto function definition. B is equal to G inverse of C. Similarly, for all B belongs to B, there exists A belongs to A such that f of A is equal to B implies A is equal to f inverse of B. Now G circle f of A is equal to G of f of A. F of A is equal to B. Now G of B. We know that G of B is equal to C. Now I am taking A. A is equal to G circle f whole inverse of C. G circle f whole inverse of C is equal to A.